from people you trust.
This is TWIT.
Bandwidth for Green Tech Today is provided by CashFly at CACHEFLY.com.
This is Green Tech Today, the TWIT Network's Top 25 Green Tech Innovators series. This episode of Green Tech Today is brought to you by the Eco-Imagination Challenge from GE. GE and its partners are awarding $200 million to ideas that help build the next generation power grid for the 21st century. For more information and to view and comment on ideas, go to ecoimagination.com/challenge. And by MailRoute. Businesses of every size use MailRoute. 1 user to 50,000 users, it doesn't matter. MailRoute will protect you from spam and viruses, simplify your life, and make your email usable again. It's estimated that just 3% of the Earth's water is naturally fresh. With populations growing around the globe, the question now is how to provide them all with fresh water. That's where companies like Boston, Massachusetts-based Oasis Water come in. Developing a technology called engineered osmosis, Oasis promises to produce clean drinking water from wastewater, cheaper and more efficiently than the competition. Water is an essential resource. And here in Boston, Oasis Water is working on a new method to get water to people more cheaply and more efficiently. I'm with Rob McGinnis. He is the Chief Technical Officer and co-founder of Oasis Water. Thanks for joining me.
Yeah, you're welcome.
Thanks. So, first steps, what's the basic technology that you're using here at Oasis Water?
The basic foundation of the technology is simply osmosis, right? So what we're trying to do is we're trying to desalinate seawater, to treat impaired waters, and we also have a power application. But just to talk about desalination, and I'm going to refer to this apparatus here behind us, there are 2 ways people have desalinated water in the past. Mm-hmm. One way you've taken a membrane, we call it semi-permeable membrane, and that allows water to pass through but not salt. And you've taken seawater and you put it under hydraulic pressure, you squeeze it through, and then the water, fresh water, comes out the other side.
And you end up with a crust of salt on the other side.
Well, you end up with a brine, right? And that discharges it back to the ocean again, right? And so, but this requires a lot of work, and it uses electricity, which can be used for anything else: transportation, heating, cooling, anything you can imagine. Electricity is quite useful for anything else. Before this was done, we simply used thermal energy to take seawater and boil the water off as steam. And so you have a pot full of seawater, essentially. You'd heat it from beneath, and then steam would rise. You condense it, and we got better at doing that, and then we had stages, right? But it still uses fairly high temperature heat that could be used to make electricity or to heat homes or do other things, right? So the principle here is different. This is a third way to desalinate water, and this is to use a 2-stage process. And the first stage uses a membrane. We have a membrane in a cell here of the same type you might use in that conventional osmosis technology where you use hydraulic pressure. But we don't pressurize our systems. Instead, what we do is simply use osmosis to effect a separation. So now
and osmosis being concentration gradients.
Right.
Not forcing, but just allowing an easy flow of water from one side.
That's right. So like in the cells of our bodies or in other organisms in the world, we have this taking place all the time. So we have a somewhat more saline solution inside of, say, a cell wall, which is a membrane, which allows water but not salts. And on the outside, there might be a less saline. And in this case, the water will flow into the cell. And if the opposite is true, if it's more saline outside, then water will flow towards more saline. In general, the water flows towards the salt, right? So what we do is we take advantage of this in our system. So we make it so that the seawater is the dilute water. So it is the lower osmotic pressure, it has less salt. And then we create a solution of salts which have very special properties. And this is the foundation, actually, of the innovation that allows us to do what we do here at Oasis. And these salts are just like sodium chloride, just like the salts are in seawater, in that they make osmotic pressure. They cause water to flow through the membrane from the seawater, which is now low, to our solution, which is now high. But what's exciting about this set of salts we've chosen is that when we go to the second step, when we heat the solution with these salts, they turn into gases, right? So this allows us to use very low temperature heat and to not make the water into steam in order to separate it. So we have a membrane system, which is passive. It's driven simply by osmosis. It doesn't really consume any energy.
Yep.
certainly no electricity other than just pumping fluids in an unpressurized environment. And then we have a step where we use low temperature energy, but not to change water to steam, but rather to change salts into gases, and it uses much less energy.
Right, because you're not having to put as much heat energy into the system.
That's right.
to create steam, to get the gases to actually form.
That's right. The amount of energy it takes to turn water, liquid water into steam is very high, and it is about 1/10 that amount of energy is required to turn these salts into gases. So the theoretical benefit is a tenfold. The practical benefit is something that we're working on here at Oasis, and we can use now between a third or 1/2 of the energy in our engineered systems, and I think we're doing better every day.
Okay, so the idea, where it came from, you were involved in inventing this. Was it inspired from biology? Where did you get the idea?
So I was actually the inventor of this basic technology. I did this as an undergrad at Yale University. And it was inspired by my first seeing a desalination plant in the Persian Gulf. I was in the Navy before I was an undergrad, and I saw these enormous desalination plants and was struck by how inefficient the description of them was. It was like, really? They just burn oil and turn all that seawater into steam and then condense it, and that's the water they drink? Yes, and that's what was done. And so when it came time for me to be a student, I was fascinated with solving that problem. I guess I sort of fixated on it because I thought it was a real opportunity to make a difference. If you look at water scarcity in the world, the amount of energy that's used to make water, the interface between energy use and water use, it's a fantastic place to do research. And so in the course of studying solubility curves and thermodynamics, I saw these two things fitting together, and I started working on it. It took me a couple of years, but when I was an undergrad at Yale, I finally came up with the solution of these thermolytic salts, these salts which create osmotic pressure but then can be turned to gases, and that was the thing that sort of made it all click.
And now you're working on it in an actual application setting. You've taken it from lab. Here we're in a lab setting, but it's in your company. So what are you doing here in your lab setting? Is this similar to what you were working on at Yale?
So this system here, this is one of our small membrane coupon test cells. So this is actually a little cartridge, and inside this is a small sheet of membrane. And this allows us to study the amount of water that goes through, the amount of salts that are rejected by the membrane, to understand a membrane sample, essentially. And we just flow one solution on one side of this cartridge. It's a little rectangular flow channel. And we just flow the other solution on the other side. You can see we have these low pressure pumps that are causing the solutions to flow. We have one solution in this container, and the other solution is inside of this container, but it's on a scale. And we have it inside the box because the scale is very sensitive, and even breeze and whatnot can influence its stability. Right, there you go. That'll show up. So this allows us to study change in mass, which tells us how much water is flowing through. So this is the apparatus that I first conceived of at Yale as an undergrad, and we still use this today. And other people in other places, other labs, and other companies in the world have replicated this sort of equipment. I can show you next some of the larger scale equipment we use, but essentially we start with the coupon and then we go to membrane modules and up from there.
Okay, is there any significance in the pink versus the blue, solutions that we're looking at?
This is so that we don't connect one to the other and just mix them.
And just a little bit of dye goes a long way towards helping your process.
Other than that, there's no significance to the color.
Okay. So let's take a look at the larger scale stuff.
Sure.
Can't wait.
We're partnering with 4 of the biggest venture capital firms in the clean energy space, 3 in the US, 1 in Europe. Again, we think that the combination of GE investment and venture capital investment is going to allow us to increase innovation. It's going to allow us to accelerate new ideas. It puts us shoulder to shoulder with some of the smartest tech investors, and we can use what I would call the industrial clout of GE to bring technologies to this marketplace faster.
GE announced its challenge at a San Francisco event along with its 4 venture capital partners. Emerald Technology Ventures, Foundation Capital, Kleiner Perkins Caulfield & Byers, and Rockport Capital Partners have all joined with GE. Ideas from companies and individuals can be entered through the ecoimagination.com website for the next 10 weeks. So check out ecoimagination.com.
Okay, so tell me what we're standing in front of here.
So this is the next size system, right? So we started with that little coupon of membrane, and we have it in a little cell about this big. But what we've done now is we've taken that same membrane in a big sheet. It comes out as a flat sheet, and we've rolled it up into a spiral wound module. And what we do is we drop that module into a container, a vessel, that allows us once again to have 2 pumps, either the same kind of pumps, just a little bit bigger.
Right.
And now instead of having a small container, we have a big tank, and we still have scales. This is a pretty convenient and inexpensive way to measure mass flow. And now what we do is we look to see, does what's happening in this larger module with, say, that might have maybe 15 square centimeters, this one might have, say, 7 to 10 square feet. And so we see, is there any sort of difference, and it allows us to study the way we make that module to make sure we're using all the area inside of it effectively. So this is the next scale, one single leaf module in a system which is pretty much the same sort of system in terms of experimental data as the coupon.
Okay. Is there, are you doing any work on the membranes themselves, or are you specifically working on?
We do, but we do that in partnership with people who make membranes, right? So
Yeah.
the idea is we think we know how to make them, we know what we need. What we need is a little different than what they're usually made for. So these membranes, these semi-permeable membranes that are used for allowing water to pass through but to reject salt, they're made for reverse osmosis, the system which takes hydraulic pressure and squeezes water through the membrane. And so we said, well, we don't need that kind of pressure resistance, but we still want the same water flux and high salt rejection. Can you can change it a little bit in these ways? And we did that successfully in our first year. And now we have a fantastic membrane, which is the best in the world at allowing water to flow and reject salts on osmosis alone.
What kind of solutions are you using in the tanks here? What are you testing currently?
Well, so we can do anything from a synthetic solution where we just mix up a bunch of salts we're interested in to actually just seawater from the ocean or water from a customer we might treat. And on the other side, we can use our proprietary draw solution or just any mixture of salts which creates osmotic pressure of the same type. And really, we can vary that as much as we like. We just pour it in and use these impellers, these mixers to mix it up and keep it the way we like. It's a very versatile test system.
To make sure that you don't have a bunch of stuff sinking to the bottom.
Well, that's right. You get density changes and you get accumulation in some cases, right? But salts have a tendency to spread out. That's what we're exploiting. But right, if we put in something which is meant to be suspended, you have to keep it that way. And you can see this is a pretty rough apparatus. This is not indicative of a product we're going to sell. This is something that's experimental for us.
Okay.
And as we move this direction, we can go to larger scale systems.
How big is this system? What's the capacity of this test system?
Well, this is designed to run perhaps for 1 or 2 full days. So we really think of it in terms of duration of test rather than say water treated. This will give you a fraction of a gallon a minute essentially, but it's designed for that because when you start to have bigger and bigger tanks, as you'll see, we have some pretty big tanks for other larger tests.
Okay, let's look at the tanks.
Okay.
I want to see them. They're over there.
So these are our large-scale tanks. This is what we use for longer duration tests. These are up to 5,000 gallons each, and so we can run a test that's maybe a week or so. We have one tank that's full of seawater now that we like to treat seawater as sort of have the roots of our technology, and we like to return to it from time to time. We also have water we've made to represent sort of pure water that we can use analytically. We've got water we might bring in from a customer and wastewater that we will dilute.
So how does this represent what you're going to be doing for full-scale installation?
Okay, so this testing apparatus is designed to give us more information about what a full-size system would be like. Now, a full-size system will use modules like this. This is a full-scale forward osmosis module. This is a module which allows us to have one solution flowing on one side of a membrane, other solution flowing on the other side of the membrane. This has a lot of area in it. It's about 250 square feet in this module, and it's a size which is like that used in reverse osmosis, so it's easy to use, equipment is easy to come by, and that sort of thing. But behind us we have a test apparatus which is actually the next step up from the last one we looked at, which is a single module with maybe, say, 7 to 10 square feet in it. We can put 10 of those into this array, and this allows us to have seawater go on one side, or whatever water we're going to treat, and have it come out the other side much reduced in volume. So we can get 75 to 85% of the water out of the seawater, depending on how we want to run the system, in a single pass, so that's not batch. And it's important if you're going to run the system as a steady state, once through system in your full-scale plants, to really understand that in your laboratory. So this is kind of the next step. And then we also characterize modules of this size, and we can correlate all that data, the coupons, the single module, the module array, the full-scale systems, and we know what the plants will do. And the great thing about these is that these are modular building blocks, so if you put, say, 6 or 7 of these in a row in a vessel and plug up the other ends and make connections, you have a lot less piping than if you did them all individually, and that is one representative piece, and you just multiply that in parallel to get to your 100 million gallons a day.
Okay. And in terms of different types of treatment, are you looking at installing different types of modules, or does this work for salt, for seawater, for wastewater, for?
There are some differences. So you change some of the things inside the module depending on the conditions you want to create. So not only thermodynamics is important to what we do, but also fluid mechanics. And so we have to think about how does water move through the flow channel? Is it very turbulent? You know, do you want to have that channel be very open, or do you want to have the water, you know, actually create a great deal of mass transfer and mixing inside the cell, or inside the channel? So we change that for different circumstances, but it always looks like this on the outside.
Okay. So they're always getting the same thing on the
Always
outside.
getting the nice pretty package on the outside.
Excellent. Now, for the future, what are you working on? Where are you going with this?
So we certainly intend to use this for seawater desalination, and I want to take the opportunity to talk about why I think that's exciting, if you don't mind. Is that currently, if you want to create water from the ocean, you have to use a great deal of energy, and that energy has to come from some resource. Now, it's either going to be fossil fuel, or you might put in, say, a wind farm and say, well, I'm going to use renewable energy, except that you're only one step removed from fossil fuel, because that wind resource itself is limited in geography, and it could have been used to displace fossil fuel. So if you're using prime energy, like electricity or very high temperature heat, to desalinate water, then you're trading energy use, emissions, you know, for fresh water, which exacerbates the problem with water scarcity, and it's a vicious cycle.
Right.
And we think we can break that. So we can actually use very low temperature heat, the kind that comes from a power plant. So if you have a power plant that is making electricity already, right, and almost all power plants, with very few exceptions, are thermal, right? So you have coal, natural gas, you have nuclear, you have solar thermal. These are all thermal processes. They all reject a great deal of heat to the environment, much more than they actually turn into electricity.
Right.
We can use that heat and 1/10 of the electrical energy that would be required for reverse osmosis. And what this means is that you can have a truly sustainable desalination solution, so you don't have to trade fuel and emissions for fresh water. And because it's such an unpressurized system that uses such low temperature heat, the cost is very, very low. So we can actually desalinate seawater for less cost and less energy than it takes to transport it through an aqueduct. Right? So if you're in Southern California, this is going to be a much more attractive option, both in terms of energy use, in terms of emissions, in terms of cost, than getting it from, say, you know, the Sierra Nevadas through an aqueduct. And it's actually less expensive than reusing sewage or reusing wastewater, which people don't really want to do, but so far has been the low-cost option. So we're very excited about seawater.
Right.
But it's not the only application. So we can take industrial waste and we can purify those, right, which is good for the environment and also less expensive than the alternatives. And we have a power application where we can actually use modules like this to turn differences in salinity into electricity. And so that's a very long and involved explanation, probably, if we were to get into it. But if you think about the fact that we can use
Ionic gradients across a membrane.
well, what's happening is you have a solution of salts inside of a water envelope, essentially. If you have a beaker full of a salt solution, that salt solution creates a pressure which is calculated the same way you calculate the pressure of gas particles inside of a container. And so essentially the water is containing those salts which want to bounce around with their thermal energy.
Yep.
And if you add more water, it will expand. And so you actually can capture the thermodynamic potential for doing work of salts just by adding some water. So you can actually go either direction.
That's interesting. That's fascinating. So potentially there could be some energy producing aspects.
As a matter of fact, we have a grant from the Department of Energy to build a heat engine based on osmosis.
Nice.
It's a $1.3 million grant, and so what we're going to do is we're going to go out and build an osmotic power plant on a geothermal resource. So one of the things that's great about the power we can make with these systems is that it can use that same low temperature heat. So we can take heat at, say, 50 degrees Celsius from a geothermal resource which is not very deep and not near a fault line, and we can make power without using any fuel. And we're really excited to build that plant. It's a great opportunity.
I think it's a fantastic opportunity. Final question, what happens to the waste? So seawater industrial waste is probably the stuff that people would be most concerned about, but what do you do with that when you're done?
Well, the trend is towards zero liquid discharge, right? So the idea is that you treat it all the way to the point where it's just a pile of salt, and you use that, you put it on roads or you put it back into chemical feedstocks, and that's easier to do with industrial waste because the volumes are so much less. When you talk about 100 million gallons a day of desalinated water, you know, there's a lot of brine. Now, we're perfectly capable of taking it to the point where it's just about ready to precipitate and then putting a crystallizer on it and turning it into salt. The question is not a technical one. The question is whether or not that is what cities want to do with their water, because then you'd have essentially barges of salt going from San Diego to Minnesota or something like that, and you know, and trying to use it on roads or use it in other industries. We could do that. If that's not what the cities who build desalination plants want, then what we can offer is we can take much more water out of what's taken in, so we can intake less, right? So there's less of an impact to the environment from taking seawater in, and we can discharge a lot less and so it's less of an impact on the brine discharge. So we can go anywhere from making it less of a problem to making it no problem, depending on what people would like.
Sounds pretty good.
Thank you.
I like it. Thanks.
Sure.
So, energy efficient, cost efficient, seems like a pretty good deal to me. Check it out a little bit more. We'll be back in just a few minutes.
Businesses of every size use MailRoute. 1 user to 50,000 users, it doesn't matter. MailRoute will protect you from spam and viruses, simplify your life, and make your email usable again. MailRoute is a secure, hosted service that filters virus and spam from companies of any size. There's nothing easier for mail filtering than MailRoute. There's no hardware or software to install. You just sign up with MailRoute to start your mail flowing through them, and then they do all the work for you. Visit mailroute.info to sign up. As a TWIT listener, you'll receive a 10% discount for the life of your account. Small business accounts start at $2 per user per month for 10 users, and because of demand from the TWIT Army, MailRoute has added a new service for individual users as well. Visit mailroute.info and sign up with the email filtering service that Tom and Leo use.
I'm here in Boston at Oasis Water with their CEO, Aaron Mandel. Aaron, can you tell me a little bit about how you got involved in this company, Oasis Water?
Yeah, absolutely. So prior to starting Oasis, I was involved in starting a few other companies with my partners at Great Point Ventures. I had the opportunity to be involved in biofuels and in geothermal power, clean coal gasification. So we looked at a number of alternative energy processes, and the theme that just kept coming up over and over again was just how much water all these alternative energy processes require. So when you compare conventional power generation to alternative power generation, a lot of times you're actually using water as an energy resource, and so you're consuming a lot of water. And so we specifically set out to try and find a technology that would allow you to reduce the cost of water treatment so that you could use more water for alternative energy, and also to use lower grade water resources to produce energy. And so that's how I originally got involved in the company and identified the technology at Yale University.
And how is this technology compared to other technologies that are already in use for desalination and waste treatment?
Yeah, so our whole goal at Oasis is to reduce the energy footprint of desalination, right? Because if you look at water scarcity globally, in 15 years, which is not a very long period of time, 2/3 of the entire planet is going to have some form of water scarcity, whether it's economic water scarcity or physical water scarcity where there is no water. And so our goal is to look at how desalination is done today, which typically is very energy intensive. There's two ways of doing it. Reverse osmosis is one way, which consumes a lot of electricity. And then there's thermal processes where you're literally just burning fuel to evaporate water. Yeah. And so the purpose of our technology is to reduce the energy footprint, which drives down the cost. And so we're targeting getting to a cost for desalination where it can be widely adopted and really serve as a primary process for producing new water resources in areas where you don't have enough of a water base.
Do you have numbers on what kind of cost efficiency, like what it costs currently for desalination and what your price point is going to be?
Yeah, so today desalination can be done for anywhere from, say, 65 cents a cubic meter on the low end, and that's oftentimes in places where the electricity is subsidized, to over $1 per cubic meter of water on the high end.
And that's a lot.
That's a lot, and that's for thermal processes as well. Okay. And that's a lot, exactly. And so our goal is to get down to about 25 cents a cubic meter. And that'll be over a long period of time as we roll out successive generations of technology, but that's our target. And we do that by really changing the energy resource that you consume. So rather than consuming electricity, which is a very expensive energy resource which can be used for a lot of other things, we focus on lower cost energy resources, fuels, and even waste heat that comes from power plants, where you can spend a lot less money on the primary fuel.
Right, so find different ways to work with the environment or the application that you're going to be installing a system into, and see where you can actually make it more efficient.
Exactly, exactly. So we can now bolt onto power plants and use the heat that they're wasting. We can bolt onto industrial facilities where they're doing a lot of power generation and use that heat. So for the same fuel, the same primary fuel resource that you're consuming to produce your goods, we can also take that same primary fuel and produce water as well. So it's much more efficient.
How about the cost versus what water costs people currently?
Yeah, so today we can talk about water scarce regions, but in California, for example, it costs about 65 cents a cubic meter just to move water from, say, the northern part of the state or the Colorado River down to places like San Diego where they don't have a lot of water. So that's the cost of just pumping the water infrastructure system to move the water around. So it's relatively expensive. And if you look at the state of California, you're actually consuming 20% of all the electricity in the state for moving that water around, for water production. And so our goal is to really get significantly below that and significantly below the cost of just wastewater reuse. There's some activities now to actually treat wastewater to the point at which it can be consumed, and we want to use desalination as an alternative to that.
Right, so consumed as more than, say, water for plants or agricultural purposes, but actually people drinking the water.
Drinking wastewater directly, exactly.
Yeah.
And that's something that is accepted in some parts of the world, like Israel and Singapore, where water's been an issue for many, many decades, but not so much yet in the United States. And so desalination is really sort of the holy grail of water production, because you can now produce an infinite source of new water almost anywhere in the world. It's always where population centers are. And it'll never run out. So if you can get the cost down, that really represents a good alternative source of water.
Yeah, where do you see this being the most beneficial in its implementation? I mean, there are areas like Israel that are, they're landlocked. They have issues with fresh water already. There are other areas that have abundant freshwater supplies. Where would it be most beneficial?
So initially, on the desalination side, when you're talking about actually making drinking water from seawater, it's going to be most beneficial in the areas where you have water scarcity. So in the U.S., it'll be places like California and Florida, and then globally, it's places like the Middle East and the Far East, where there's always been a water scarcity issue. But initially, with Oasis, we're going to start by focusing on industrial applications. So there's a lot of heavy industries that consume a lot of water or produce a waste stream that's very high in salts, where they need to recover that water or reduce the volume of the waste stream. So we're actually going to focus on a solution for the heavy industries first before we go to the municipal markets, where the adoption cycle for new technology can be a little bit more conservative.
Right, and where you'd probably have to also build giant plants as opposed to installing into an already existing industrial plant.
Exactly. So one of the keys to getting a new small business off the ground is focusing on something that you can do in the near term. And so the industrial applications are smaller scale. There's tremendous demand. You're working with customers that really want to adopt a new solution because they have a real need. And so it's something that we can do in a 1 to 2 year period of time, instead of waiting for the 3 to 5 year cycle, where cities like Boston that have municipalities that are more conservative are willing to say, well, let's take a look at a new desalination approach.
Right. What have been the biggest challenges to getting this company off the ground and starting to get people looking at adopting it?
The biggest challenges, I would say, are just actually introducing a new product into the market. So I would say that on the technology side, we've had great success scaling the technology up from small prototypes, proof of concept, to pilot systems, and then on to demonstration plants. But the challenge is really building a new business and getting a product in the market that customers are willing to accept and adopt and grow the business that way. But we have a great investor base, and we've got a great team of people that actually come out of the water industry, and those things are really important when you introduce something like this.
Where do you see your company in about 10 years?
10 years? Well, we expect to build a new water business. So we have several applications of the same basic technology. It can be applied to industrial water reuse, which is what we're starting with. So taking raw wastewater and in a single process producing potable quality water that can either be consumed or used for industrial purposes. We can use the process for desalination to make drinking water at a large scale. And then we can also use the process for power generation. So there are applications of this technology for producing a new form of hydroelectric power using salinity difference, osmotic pressure. So we see a number of avenues that we can go with this technology, and so our goal is really to build a standalone business that would leverage this technology to make a dramatic impact on the overall energy footprint for water production across the globe.
And do you see Oasis Water being a large part of the solution to the water energy situation that seems to be creeping up on everybody?
Yeah, we do. So we see our technology as a way to use different forms of energy for desalination. It doesn't make sense to be burning fossil fuels and have that environmental impact and that cost, and then turning around and using the electricity that you produce to then produce water that has to then go back and be used for power generation. So we think we can make better uses of the primary fuel. And we also think that there's a lot of applications where our technology sits at the nexus of producing water specifically for energy processes. So there's a big push that we have to integrate this technology specifically into power generation systems, so that when you buy a turbine or you buy an industrial engine or you buy a boiler, it actually has this technology built into it so that it has reduced water footprint. And that's going to be important for a lot of Fortune 500 companies that operate in water scarce regions, which is typically all the places where you have low cost of labor. There's a correlation between manufacturing cost and water availability.
All right, well, this seems like a pretty beneficial technology to me, and I wish you a lot of good luck.
Oh, thank you very much.
You're welcome. Thanks for the interview.
Thank you.
So that about does it for this week's Green Tech Today. We've covered some water technologies that here at Oasis Water that might be taking us into the future with more available water for everyone. It's something we really need to look into. I'm Dr. Kiki. I'm done green hunting for this week, so catch me someplace new and exciting next time.
That's it for this episode of Green Tech Today. Subscribe at twit.tv/GTT and never miss a show. If you have a question or a comment, email us at greentechtoday@twit.tv. Or you can leave a voicemail at 415-GT-TODAY.